This lecture is on electric potential energy. It says, if I wasn't an actor, I think I would have gone mad. You have to have a bit of extra voltage, some extra temperament to reach certain heights. Art is a little bit larger than life. It's an exhalation of life, and I think you probably would need a little bit of touch of madness. So we're Laurence Olivier, a famous actor. So what we're going to do is we're going to relate what we've learned about electricity so far back to what we learned about in terms of the law of conservation of energy. You should be able to relate the electric force back to energy. You should be able to differentiate between electric potential and electric potential energy. And those are they sound very similar, so you need to be very careful with that. You need to understand the chemistry that's involved in a battery. Now, we're not going to go back into a whole bunch of chemistry, but just the general chemistry involved. And you need to be able to calculate the electric potential and electric potential energy given a situation. Number one, electrical potential energy. Just like gravity results in potential, electrostatics result in a potential to move. If I take a book and I lift it over the ground and I let go of it, the object will start to fall. So we say that the book has gravitational potential energy because if I let go, it'll fall down. Well, electrostatics are the same way. If I bring a proton and another proton close to each other, if I were to let them go, they would move. They would move away from each other because of the electrostatic force. So we call that the electric potential energy, or the potential energy due to charge. So you can actually have a potential that's positive, okay, which would repel, or negative that would attract. So it's a little bit different than gravity, but it's the same basic idea that if you let go, what will it do? Now, remember, we had the law of conservation of energy. We said the potential energy of position is equal to work. What do you do in order to get there? We said work is force times distance, and if you're lifting a book in this case, the work you do in lifting the book is equal to the gravitational energy that you have. Or the work that you do compressing a spring is the elastic potential that you have. Well, we can do the same thing here. We can say the work that you do is equal to the electric potential energy that you have. So if you take a proton and you move it closer to another proton, the work that you do to get it to that position is equal to the electric potential energy of that object. Well, if you were to take this formula right here and you were to put it in terms of electrical values that we've talked about so far, as far as force and distance and things like that, you get a couple of different formulas. And the formulas are this. The potential energy that's electric is equal to QED, which is the charge of the object, the electric field of the object, and the distance. Okay? Or what you can say is it's KQ1 Q2 over D. Okay? That right here is, if you look, E is force divided by charge. So if you have force divided by charge, that right there, the charges would cancel out and you have force times distance, which is where this formula comes from. It comes from the fact that work is force times distance, and force would be the electric field times the charge. So that's where we get this formula right here, and this is the formula for electric potential energy. Potential energy, just like any other energy, is measured in joules. Now, electric potential energy is useful sometimes, but more often we're interested in something called voltage. Voltage we will talk about much more when we talk about electric circuits, but it's basically the electric potential energy expressed on a per charge basis. So how much energy does one charge have when compared to another charge? And that's what we call voltage. Voltage has a bunch of different names. They call it electric potential, they call it potential difference, they call it voltage, they call it the electromotive force, they call it all kinds of things. But basically what it is it's the energy, the electric potential energy divided by charge. So it's the energy on a per charge basis. Well, whenever you do that, it actually simplifies down to where it's just K, Q over D. And that's another expression for the voltage. So we have a lot of formulas here. We've got this one right here for potential energy, and we've got this one for voltage, but they're all related to one another. So if you can kind of see the commonalities between them, it makes it a lot easier. Now, the most common source of voltage that we'll talk about is a battery. A battery basically has a positive terminal and a negative terminal. And what that is it's just a series of solutions, one which has positive ions and one that has negative ions. And Remember, everything wants to get to zero. That's kind of the basis behind most of what we learned in this class, is everything wants to get to zero. So the electrons can actually flow from the negative solution into the positive solution to try and cancel everything out. The voltage is that kind of that push, whatever that energy that pushes the charge through this wire to get there to the other side. Now, hopefully you can relate the electric force back to energy, and you can say, okay, the electric force moves a charge, so it's equal to the work, which can be thought of as electric potential energy. You have to be able to differentiate between the electric potential and electric potential energy. Remember, electric potential, or voltage, is just this energy per charge. You need to understand that there's chemistry involved in a battery, and that there's a positive solution and a negative solution, and the ions flowing from one to the other is actually how you create that voltage. And you should be able to calculate the electric potential and the electric potential energy given a situation.